This problem is a bit convoluted, and finding the answer or finding the pathway to the answer is not readily viewable. So what we're going to do is we're going to start off by just showing what we do know. So we're going to say t naught is 0. That's going to be an obvious. We're going to say x naught is 0 just to kind of complete the picture here. The coefficient of static friction is 0.60. The mass of the block is 2.0 kilograms. And the velocity of the train is 0.05 meters per second. So even though I don't label this the best, because sometimes we're talking about the block, sometimes we're talking about the train, we're going to have to keep this in mind and keep our eye on the problem while figuring out the solution. So these subscripts hardly do us any justice. Lastly, the spring coefficient is 50 newtons per meters. What we need to find is the amount of time it takes for the block to start moving. So obviously, I'm not going to write time for block to start moving in the subscript, but at least I know I have a list of things that the problem gave me. The path I'm going to take seems like I want to first find the maximum friction before the block starts to move, because I know that the train is going to pull on a string, which is going to pull on the block. And I want to know what the max static friction, I guess, can keep the block from moving before it budges, right? So max static friction before motion, and then perhaps I can use that to see how much time it took to achieve that maximum static friction, to achieve it. Okay, so that's my game plan, and let's see if it works. Okay, first, anything with friction, and I guess essentially any scenario requires Newton's second law. So since we're talking about one dimension, right and left, we're going to say that the sum of all forces in only the x direction, so I'm not going to put a subscript, is mass times acceleration. And since we're talking about the time it takes to achieve a breaking of static friction before the block goes into motion, the entirety of the problem is going to be motionless. Once motion happens with the block, the problem's ended. So we say 0 for acceleration in this case. There are two forces acting on the block. There is friction pointing this way, and there is spring force pointing this way. Don't pay attention to the length of the arrows. Okay, so we have spring force minus friction force. And when I say friction force, we really talk about the maximum friction force before it breaks and turns into kinetic friction force. That's going to equal to 0, which then obviously means that spring friction has to equal to the static friction force before it breaks. So when does the spring force end up becoming the static friction force? How much time does it take to achieve that? Okay, well, to achieve that, let's go ahead and look at the breakdown of spring force. It's going to be K delta X. Okay, that's Hooke's law. And that's going to equal to mu static times normal force. Now, again, anything on a flat plane that doesn't move up or down means that the normal force ends up equaling to gravitational force, which is just going to be mg. So let's go ahead and skip a few steps knowing this, and we say that K delta X is equal to mu S mg. Cool. But where does this take me? This takes me nowhere because I don't know how much time. There's no time factor in this equation. Well, I think about this a little bit more and I say, well, we're looking for the max when the spring force ends up being the same as the friction static force breaking point. And it only happens when this parameter reaches a point where, this can be fulfilled. So I'm thinking, well, the train is going over to the right, thus, at a rate of 5 centimeters per second. increasing this, right? Increasing the delta X, the stretching of the spring, so that it could break that static friction force. So I'm going to go ahead and just say, well, I know that V is delta X over delta T. I know what V is, so perhaps I can go ahead and turn delta X's to a function of V and delta T. And that's actually going to give me, in that case, the T it takes to achieve this scenario that we want to happen. So K times V delta T is then equal to mu S mg. And right now you can see that the delta X turns into V delta T via this kinematic definition. Well, that's great. This is how much time it takes for this condition to be met. So let's go ahead and isolate delta T. It's going to be mu S mg divided by K V. And we know all the factors. We all know all the quantities. We know that ms is 0.60. We know the mass of the block to be 2.0 kilograms. We know the spring constant to be 50 newtons per meters. And we know the velocity of the train to be 0.05 meters per second. This is great. So now we know everything. So delta T, after putting it into a calculator, is going to equal, it's going to end up equaling 4.7 seconds, accounting for the significant figures. So we now have the amount of time it takes for this condition to be met, for the spring force to equal to the breaking point of static friction force, and thus for the block to start moving.